So if you want to look at collisions in two dimensions, and this is just kind of like what we did with kinematics, motion in two dimensions. Conservation of momentum is a vector, and so conservation of momentum implies that momentum is conserved in the x direction and momentum is conserved in the y direction. So kind of just what we did with kinematics. We could treat the x and the y separately and then put them together at the end if we want. And so this equation would become P1 final x plus P1 final y. Sorry, got that one wrong. P2 final x equals P1 initial x plus P2 initial x. In other words, the initial momentum of the x direction for the two objects adds up to the final momentum in the x direction for the two objects. Similarly, P1 final y plus P2 final in the y direction equals P1 initial in the y direction plus P2 initial in the y direction. You can just apply the momentum, the conservation momentum along each axis independently. So this is a little harder problem. This is a two-dimensional collision problem. M1 equals 5.5 kilogram bowling ball with V1 initial equals 9 meters per second collides with 0.85 kilogram pin, a bowling pin, with V2 initial equals 0. In other words, it's at rest. And then I should say which is scattered at V2 final equals 15 meters per second at an angle of 85 degrees from V1 initial. And this is what's the velocity, final velocity of the bowling ball, and they want the magnitude and direction, right? So let's just draw a picture of it. So we'll put the bowling ball, this is M1, and it's traveling around down this way, right? And it's got V1 initial equals 9 meters per second. It's traveling this way. I'll set up my coordinate system like this. This is y and this is x. And then it gets to here, right? And it collides with a pin. And so this is a pin. This is M1, and that guy is M2. And M2 goes off in this direction, and so that's V2 final, right? V2 initial was 0, right? It was at rest. And so the direction for V2 final, right, this is, I'm going to call this theta 2. I'm not doing a very good job making that angle. So if this guy is going that way, I can say that direction is 85 degrees, right? That's V2 final. And as a result, V1 final will kind of go off this way. And so I've got the initial momentum of the ball going this way. This guy's at rest, so it doesn't matter. M2 is at rest. And then after the collision, I know the velocity and direction of the pin, and they're asking me for the velocity and direction of the ball, right? V2 final is 15 meters per second, and the direction is 85 degrees from the horizontal. And so if I sort of make my general statements, if I say, look, P final equals P initial, and I should make these as vectors since they're in two dimensions now, then that means P1 final plus P2 final, right? The momentum of this guy plus the momentum of that guy equals P1 initial plus P2 initial. We can make a mental note that this guy is 0 because initially he's not moving. And so then I can break these up into x and y components, and I can say P1 final x plus P2 final x is equal to P1 initial x plus P2 initial x, right? Again, this guy is 0. And similarly, I can say P1 final y plus P2 final y equals P1 initial y plus P2 initial y. And notice both of these are 0, because initially the bowling ball has no velocity in the y direction, and the pin is at rest, so it has no velocity in the y direction. So this is going to give me a pretty simple equation, and we'll just have to see what we learn from these guys. I'll do this on the next slide. And so what I said was P1 final x plus P2 final x is equal to P1 initial x plus P2 initial x. And so that one's just M1 V1 final in the x direction plus M2 V2 final in the x direction equals M1 V1 initial in the x direction plus M2 V2 initial in the x direction. This piece is 0 because this guy starts out at rest. V1 initial in the x direction is the initial velocity of the bowling ball. That's just V1 initial, and that's what we said was 9 meters per second. Right. And so that says that let me redraw my drawing here. This is M1. Goes this way. Right. This is M2. This is theta, and so this is V2 final x. This is V2 final y, right? And so V2 final x is equal to V2 final sine theta 2, and that's equal to 15 meters per second times the sine of 85 degrees. Which is 14.94 meters per second. And then V2 Okay, so here's my 9 kilogram bowling ball traveling at 5.5 kilogram bowling ball traveling at 9 meters per second. So this is M1 equals 5.5 kilograms. And then M2 is 0.85 kilograms. So M2 equals 0.85. And V2 final is 15 meters per second. And so we're given the initial velocity of the bowling ball, the fact that this guy starts out at rest, the bowling pin starts out at rest. We want to know the magnitude and direction of the two other velocities. And so on the previous video, we broke it up into x and y components, and now I can say, look, this becomes M1 V1 final cosine theta 1 plus M2 V2 final cosine theta 2 equals, and since the pin starts out with no velocity at all, this guy's just 0, and this is M1 V1 initial, right? That's just, this guy's going right along the x-axis. And so we know the masses. We don't know the final velocity. So we know these masses, we know the initial velocity, we know theta 2, and we know V2 final. The things we don't know are V1 final and theta 1. And so this is one equation, and we need a second equation because we've got two unknowns. Anytime you have two unknowns, you need two equations. And so I'm going to say P1 final y plus P2 final y is equal to P1 initial y plus P2, 2 initial y. That is to say, this is conservation momentum. In the x direction, this is conservation momentum. In the y direction, that's true no matter how we pick our x and y, but we've chosen them this way. And so we can notice, first of all, that the initial y velocity for this guy is 0, so he gets a 0, and the initial y velocity for this guy is 0, right? Object 1 is moving along the x-axis. That's how we chose our x-axis. And object y is stationary. And so this just gives m1 v1 final sine theta 1 plus m2 v2 final sine theta 2 is equal to 0. And so once again, I know all of my masses, right? I know V2 final, that's the thing that's 15 meters per second. I know theta 2, that's 85 degrees. That's this guy, 85 degrees. They gave us down the problem. So once again, the things I don't know are these two guys. But now I have two equations, right? I have two equations and two unknowns. So two equations and two unknowns is solvable. And so I'll work through the algebra on this and just show you one way. There's lots of ways to solve this, but I'll show you one way. What we usually do is we pick a variable here and solve for it and then substitute into the other equation. So let's number these equations 1 and 2. And we're going to take this on from a purely mathematical standpoint. These are the two variables we don't know, theta and V1 final. And so I'm going to start with this equation, and I'm going to solve for those variables. I'm going to say m1 V1 final cosine theta 1 is equal to, and I'm just going to move that to the other side, so I'll have m1 V1 initial from here minus m2 V2 final cosine theta 2, right? And then I'm going to divide both sides by m1, and that's going to leave me just v1 cosine theta 1 here. These are the two things I don't know, right? And then I'm going to substitute in here and solve. This is 5.5 kilograms times 9 meters per second minus 0.85 kilograms times 15 meters per second times the cosine of 85 degrees. Am I still on the screen there? Now I am. All right. All divided by 5.5 kilograms. And what this gives me is V1 final cosine theta 1 is equal to, when I work that out, I get 8.8 meters per second. Again, now I still have two unknowns, but I have a simpler equation. I've plugged in all my numbers. Similarly, so this is equation 1, right? I can do the same thing with equation 2, this one, and I can say, look, m1 V1 final sine theta 1 is equal to, and I'm just going to move that to the other side and say minus m2 V2 final sine theta 2. Again, I'm going to divide both sides by m1, and that just gives me V1 final sine theta 1 is equal to minus 0.85 kilograms times 15 meters per second times the sine of 85 degrees all over 5.5 kilograms. And this gives me minus 2.3 meters per second. And so I'll just put it up here. I get V2 final sine theta 1 is equal to minus minus 2.3 meters per second. And so now I've plugged all the numbers I don't know, and now I have two equations and two unknowns, and I can substitute and solve this in a variety of ways. The way I would do this is I would take this equation, so I'd say V2 final sine theta 1 equals minus 2.3 meters per second, and I would divide it by this side. So I divide this side, sorry, that's not V2 final, that's V1 final. It was V1 final. So this is V1 final, those are the two unknowns I don't have, over V1 final cosine of theta 1, and that's equal to 8.8 meters per second. So once again, I'm telling you what I did. These are the two equations I have. This is the rewrite of equation 1, and this is the rewrite of equation 2. Again, I was solving for my two unknowns, which is V1 final and theta 1. In each of these, I just got as little as I could besides them. And now I've got these two, and I want to solve somehow, and so I recognize that if I divide the left-hand sides, since they're equal, I can divide this by that, and this by that, and it's still equal, or vice versa. And so I'm dividing this guy by that guy, and I'm dividing this guy by that guy, and that's what I show down here, because I've done enough algebra problems that I kind of know a few tricks on how to solve. But you could do this any way you want. You could solve this for V1 final by dividing by the cosine, and then plug in here and do it that way. There's a wide range of algebraic tools you can use. So when I do that, these guys cancel, and I get sine theta 1 over cosine theta 1 is equal to minus 0.261. Sine over cosine is tangent, and so I have tan theta 1 is equal to minus 0.261. And so then I can say theta is equal to the inverse tangent of minus 0.261. And that's equal to, that's theta 1, is minus 14.6 degrees. And then I can say, I can grab this equation. I can say V1 final is equal to 8.8 meters per second over cosine of theta 1, which is 8.8 meters per second over cosine of 14.6 degrees. And that gives me 9.12 meters per second. So I get my answers to this are V1 final is equal to 9.12 meters per second, and theta 1 is equal to minus 14.6 degrees. The next question I ask on this problem, so those are my answers. That's the speed of this guy, and that's the angle, right? V1 final is going this way, and that's the angle. The next thing they ask on this problem is the collision elastic? And you can tell right away that it's not, because this guy's velocity, the ball's velocity after the collision, is greater than it was before the collision. Now, it's hard to find where that energy might come from. Both of these guys have kinetic energy. Remember, the kinetic energy is 1/2 mv squared. And so I could add up the two kinetic energies, but I already know that this guy, since he's going at 9.12 meters per second instead of 9 meters per second, that he has more kinetic energy, just this ball by itself, than I started with. And so that energy had to come from somewhere. Usually in bowling, extra energy comes from spin. And so this ball probably had, in this collision, some rotational kinetic energy because it was spinning as it was going down the aisle. And that contributed to the fact that it's going faster after the collision, and the pin is traveling at a high speed after the collision. All right, that's a fairly complicated problem, but mostly because we ended up having to solve a lot of algebra here, right, to get the answer. Just getting it to this point, however, is not that hard. Breaking down in terms of the x and y components and writing down the equation to this point it should be fairly straightforward. The act of actually going through all this stuff and not making any mistakes is a little more challenging, but it's just an algebraic challenging. It's just like putting together a jigsaw puzzle with 100 pieces or 1,000 pieces instead of 100 or something. You just have to be more careful for a long period of time. So the last section we're going to talk about in this chapter is rocket propulsion. Rocket propulsion is kind of a conservation of momentum argument, but you can also look at it as a Newton's third law thing, since that's also conservation of momentum. Here's what happens to a rocket. A rocket pushes fuel out the back, and so I just have a VE, which is the exhaust speed. Of the fuel, right? Fuel gets shot out the back at some speed, and so the change in momentum, delta P for the exhaust, is equal to the amount of mass I send out times the exhaust velocity. In other words, if I'm looking at it from the rocket standpoint, when the fuel is in the rocket, it's at rest, and so its initial velocity is 0, and then all of a sudden I push down the rocket and it's got a exhaust velocity of this, and so its change in momentum is however much mass there was there. I just in 1 second say I send out a delta m. The change in momentum went from 0 to whatever that mass is of fuel in that period of time times whatever the exhaust velocity is, right? And so if you remember, that's equal to the force times the change in time, and so I'll call it the force on the exhaust times the change in time, right? But so that means that the force on the exhaust is equal to change in momentum of the exhaust over the change in time, right? Well, the thrust force is just the equal and opposite force of this. This is equal to the force on the rocket, and so the magnitude of that is the same thing. It's delta P on the exhaust over delta T. The only difference is the thrust and the thrust force on the rocket goes this way, and the force on the exhaust goes this way, right? The exhaust gets pushed out, so the rocket gets pushed forward, and that's the idea. The faster I can make this fuel go out, or the more fuel I can shoot out per time, the greater my thrust, right? The greater change momentum of the fuel, the greater the thrust on my rocket. And so I also have a force of gravity on this rocket, Fg. And so if I do the sum of the forces in the y direction on the rocket, I get the thrust force minus the force of gravity is equal to the mass times the acceleration in the y direction of the rocket, but that's just the acceleration of the rocket, right? If I want to draw my little coordinate system, like I have a little 3-body diagram there, I can. And that gives me the thrust force minus mg is equal to ma. I'm just going to call it a now, since that's all my acceleration is in the y direction. But this is just the change momentum of the exhaust over the change in time, minus mg is equal to ma. And this is just delta m times the exhaust velocity over the time, minus mg equals ma. If I divide through by m and reverse the order, I get the acceleration is equal to delta m times the velocity exhaust over the mass times the time, minus g, or I can write this as velocity exhaust divided by the mass of the rocket times delta m over delta t. That's the rate at which exhaust is being shot out, minus g, and that's my acceleration. And so if I know the rate at which fuel is being shot out, am I shooting out 10 kilograms a second, or 30 kilograms a second, or 1,000,000 kilograms a second? I know the mass of my rocket. I know the exhaust velocity, how fast it's going out the back, or if I do, I do this calculation, subtract g, and that tells me the acceleration. And so let's do one. Right, I'll just leave that equation there for a second. And this is Saturn V, the rocket that launched people to the moon. So a Saturn V rocket has a mass that's 2.8 times 10 to the 6 kilograms, and That's the fuel burn rate, right? Saturn V rocket has a mass of 2.8 times 10 to the 6 kilograms. That's just the whole mass of the rocket, right? And a fuel burn rate, delta M over delta T, how fast it's shooting fuel out the back, is 14,000 kilograms a second, right? So Saturn V rocket has a mass of 2.8 times 10 to the 6 kilograms, a fuel burn rate of 1.4 times 10 to the 4th kilograms per second. If the exhaust velocity is 2.4 times 10 to the 3rd meters per second, what's the rocket's acceleration? So I'm just plugging into this formula, right? I get the acceleration is equal to the exhaust velocity over the mass of the rocket times the fuel burn rate minus g, right? And so that's 2.4 times 10 to the 3rd meters per second divided by 2.8 times 10 to the 6th kilograms times 1.4 times 10 to the 4th kilograms per second minus 10 meters per second squared. Right. I get about 2 meters per second squared. If I use 9.8 there, I would get about 2.2. But that's my acceleration. This is how rockets work. They just push stuff out the back, and that creates a steady force on them moving forward, and so they accelerate. If you wanted to do a more sophisticated version of this, you would have to take into account the fact that as the rocket is accelerating, its mass is decreasing. And so if it keeps burning fuel at the same rate, if this number stays constant, right, and this number stays constant, then this number is going to be steadily decreasing. It's going to be decreasing by 1.4 times 10 to the 4th kilograms every second. And so as it gets higher and higher, it'll go faster and faster and accelerate at a greater and greater rate because this mass is getting smaller and smaller.